In this part of section 13.3, we're looking at higher order partial derivatives. This is sort of like taking the second derivative. The function z equals a function of x and y has the following second partial derivatives. If you differentiate twice with respect to x, you can write it as the partial with respect to x of the partial with respect to x of the function. Or you can write it using this notation or using the subscript notation. What this means is you start off with a function, take the partial derivative with respect to x, and then whatever the result is of that, take the partial derivative with respect to x again. You can do the same thing for finding the partial derivative with respect to y and then taking the partial derivative with respect to y again. Those are your higher order partial derivatives. Now, if you differentiate first with respect to x and then take that result and differentiate with respect to y, we call this a mixed partial derivative. A mixed partial derivative. You take it with respect to x first, and whatever the result is, take the derivative of that with respect to y. If you take the derivative with respect to y first and then with respect to x, this again is another mixed partial derivative, except the order is different. You take the derivative with respect to y first and then with respect to x. Here's an example of finding the second partial derivatives of this function of x and y equals 3xy squared minus 2y plus 5x squared y squared, and determine the value of this mixed partial derivative evaluated at the point -1 and 2. So let's find the partial derivatives. We first begin by finding the first partial derivatives. Take the partial with respect to x. You treat x as a variable and treat y as a constant. So the derivative of this first term, 3xy squared, is 3y squared. Treating x as a variable and everything else as a constant. So the derivative of just 3x is 3 times this constant. When we treat x as a variable and y as a constant, the derivative of 2y, the derivative of a constant, is 0. And then finally the derivative of 5x squared y squared with respect to x. Take the derivative of 5x squared, which is 10x, times y squared. And the partial derivative with respect to y is found by treating x as a constant and treating y as a variable. So this is going to be 6xy minus 2 plus 10x squared y. Those are your first partial derivatives with respect to x. The second partial derivatives, we're going to continue to take the derivative of those results. The derivative, the partial with respect to x and x again, go to this first result and take the derivative of this with respect to x. You treat x as a variable and everything else as a constant. The derivative of 3y squared, treated as a constant, is 0. And the derivative of 10xy squared is 10 times y squared, the constant, treating it as a constant. The second partial with respect to y, we have the derivative of 6xy is 6x, the derivative of minus 2 is 0, and the derivative of 10x squared y, we treat all of this as one big constant in front of the y, and we get that derivative as 10x squared. So these are your higher order partial derivatives, and we can also find the mixed partial derivatives. To find the mixed, this originally we took the derivative with respect to x. Now whatever this result is, take the partial derivative of this with respect to y. And we would get that the mixed partial derivatives, f with a subscript xy, is 6y plus 20xy. And the mixed partial derivatives, if you use the other order, you also get 6y plus 20xy. Let's go back and look at that for a second here. The derivative of this with respect to y is 6y plus 20x. The derivative of this with respect to x is 6y plus 20x. I'm sorry. The derivative of this with respect to x would be 6y plus 20xy. So you can see how we get these mixed partial derivatives, and they end up being the same. We want to evaluate this mixed partial derivative given at the point -1, 2. We plug in -1 for x and 2 for y, and we simplify the result to get -28. That is evaluating a mixed partial derivative at a given point. Here are some examples that I'd like to work through with you. For this one, we want to find all partial derivatives and higher order partial derivatives for this function. So we're going to find the partial with respect to x, the partial with respect to y, and those higher order partial derivatives. And there's 4 of them. So we want to find 6 altogether. Go ahead and try these on your own, pause the video, and come back and check your answers. Okay, to find the partial derivative of this function, f with a subscript x, that's a partial derivative with respect to x. We're going to treat x as a variable and the y's as a constant. So the derivative of x squared y is 2x times that constant y, 2xy. And the derivative of y, e to the x squared, we're going to treat y as a constant, and the derivative of y, that constant, times e to the x squared is e to the x squared times the derivative of the exponent, which is 2x. That is our partial derivative with respect to x. Now you can write this, simplify it just a little bit. You can write it as 2xy plus, bring that 2x out in front, 2xy e to the x squared. You can even factor out a 2xy and write this as 2xy times the quantity of 1 plus e to the x squared. That's one way of looking at it. All right, let's go ahead and find the partial derivative of the function with respect to y. So when we do this one, we're going to treat y as a variable and treat the x as a constant. So the derivative of x squared y is a constant times y is the constant, x squared, plus the derivative of y times e to the x squared. E to the x squared is a constant. We're treating this as y times a constant, and the derivative is e to the x squared. So those are your partial derivatives with respect to x and y. Those are your first partial derivatives. Let's work now on finding the higher order partial derivatives, beginning with fxx. That's your second partial derivative with respect to x. You take the partial derivative with respect to x and take that result. Take the partial derivative of that again with respect to x. I've copied this from the previous slide. We found that the partial derivative with respect to x, when we simplified it, was this. Now we can take the derivative of this again with respect to x. We should use the quotient rule, the product rule, sorry. We're going to take the first times the derivative of the second, and the derivative of 1 plus e to the x squared is going to be e to the x squared times the derivative of the exponent, which is 2x. So that's the first times the derivative of the second, plus the second times the derivative of the first. So 1 plus e to the x squared times the derivative of the first, treating x as a variable and y as a constant, and that derivative is 2y. We can use algebra to simplify this. Let me move this out of the way. Okay, let's simplify this by distributing the 2xy and distributing the 2y. We can simplify this 2xy times e to the x squared times 2x. That's going to be 4x squared y e to the x squared. Then we distribute that 2y. We're going to get 2y plus 2y e to the x squared. Right, so we can leave it like that. You can factor out a 2 here, or actually you can factor out a 2y here if you like. and get 2y times the quantity, 2x squared, e to the x squared, plus 1 plus e to the x squared. So that would be your second partial derivative with respect to x. Let's find the second partial derivative with respect to y. Well, our first partial derivative with respect to y we found earlier was equal to x squared plus e to the x squared. We treat y as a variable and everything else as a constant. When we take the partial derivative with respect to y and y again of this, we're going to treat y as a variable and treat x as a constant. The derivative of x squared, if x is a constant, is 0. And the derivative of e to the x squared, again if x is a constant, is 0. So this second partial with respect to y equals 0. Now let's find the mixed partial derivatives. Okay, finally let's find the mixed partial derivatives. Fx, y, you take the partial with respect to x first and then with respect to y. So take the result of what we did up here, the partial with respect to x, we're going to treat y as a variable and everything else as a constant. So this is a constant times y times a constant. This is all one constant times y. So the partial derivative with respect to y will be 2x times 1 plus e to the x squared. That's your mixed partial derivative f subscript xy. To find fyx, your mixed partial derivative, where you take the result of your partial derivative with respect to y and then take the derivative of this with respect to x. In this case, we're going to treat x as a variable and y as a constant. So we're going to take the derivative with respect to x is 2x, and the derivative here of e to the x squared is e to the x squared times the derivative of the exponent, which is 2x. Now you will notice again that this mixed partial derivative fxy of xy is equal to that mixed partial derivative fyx of xy. So these end up being equivalent if you distribute the 2x.